Good morning, everyone. It gives me immense pleasure to be here for the Aircraft Stability and Control course. I am Dr. Yagya Dutta Dwivedi, Professor from Institute of Aeronautical Engineering, Hyderabad, India. Today I am in the lecture number 4, and in this I am going to discuss about wing contribution in longitudinal static stability. Before that, we have discussed in my previous classes about type of stability. So in type of stability, we have seen that there are two types of aircraft stability. One is the static stability, another is the dynamic stability. In static stability, we have seen that if the tendency of the disturbed position of the aircraft is to revert to its equilibrium position, then we say that it is a statically stable. If the tendency is to go away from its equilibrium position after disturbance, then we say that it is a statically unstable. And if it maintains in the same location as it is disturbed after disturbance, then we say that aircraft is neutral stable. After this, we have seen the aircraft aerodynamic forces like lift and the drag. Then we have seen the pitching moment, and we have also seen the different derivatives. We have learned different derivatives of aircraft stability like Cm alpha, and we have also seen that the criteria for aircraft stability, and we have seen for longitudinal static stability the Cm naught should be greater than 0 or positive value, and the slope of the curve of Cm versus alpha, that is called Cm alpha, should be negative. If we are able to meet this situation, we can say that aircraft is statically stable. In longitudinal case, we are only talking now only longitudinal aspects of the aircraft. There are other aspects like lateral and directional. As of now, we are not discussing. In due course of time, surely we are going to discuss about lateral and directional stability also. In today's class, I am going to discuss about introduction and the review, then Cm naught and the Cm alpha, symmetrical and cambered airfoil, Cm plots, Cm of horizontal tail, clarification on mean camber C bar, then wing contribution and mathematical expression. We will derive in this mathematical expression, and then what is the physics behind the wing contribution, and how as an engineer we should design our wing. These are very important for this today's lecture, and we should try to understand very well. So in my previous classes, I have covered the following topics: introduction to stability and the control, access system, control surfaces, definitions like equilibrium, stability, controllability, and maneuverability, types of motion and stability, longitudinal static stability, applied forces and moment, lift theories, then moment, aerodynamic center, and center of pressure. These all points in detail I have already discussed in my previous 3 or 4 classes. Now here I am going to discuss about very important parameter of Cm naught and Cm alpha. I have already discussed, and we have seen that what is the meaning of Cm naught and the Cm alpha. You might have remembering that for having the longitudinal static stability, this Cm naught it is the coefficient of moment at zero angle of attack. So it should be positive. So first case, if I am drawing here one Cm versus alpha. So Cm naught means this is at alpha 0. It should be somewhere here positive. So this is called Cm naught. So first condition of longitudinal stability is greater than 0. And the second condition is Cm alpha should be less than 0. Or here I will write positive and here I will write negative. Okay. So this should be positive and this should be negative. If we are able to make like this, it means aircraft is longitudinal stable. So here we have find out this point. So this our plot should go like this. So here Cm alpha is less than 0. This is the condition. So Cm naught and Cm alpha, we need to discuss about Cm naught and Cm alpha. Here Cm alpha is change of coefficient of moment with change of alpha or angle of attack. Let us cross check for symmetrical airfoil wing. I have shown here the symmetrical airfoil. Case 1. Case 1, when the center of gravity is ahead of the aerodynamic center for symmetrical airfoil. Okay, so here, this is the diagram. This point is here, this here. This is the CG point and here is the AC point. CG is ahead of the aerodynamic center. So here Cm is equal to Cm naught plus Cm alpha. Cm alpha into alpha. Comparing with y is equal to C plus mx. At alpha is equal to 0. There we any Cm. You see here. At 0, any Cm is there? No Cm. No Cm. For symmetrical airfoil, so Cm is equal to 0 at angle of attack 0. So Cm is equal to 0. We got the point A in this plot. If you see Cm versus alpha, this plot where angle of attack is 0 and the coefficient of moment Cm is also 0. So we got the point A. If angle of attack is increased to positive direction here in this direction, Cm will be negative. So here this Cm is negative. And anti-clockwise moment will generate. So here your moment will be in this direction, or Cm alpha is less than 0 or negative as it is in this plot. The slope of dCm by d alpha is less than 0 as shown in the plot. Next case for this cambered airfoil, when CG is ahead of the AC for the cambered airfoil, at AC where the CMACW is less than 0, at alpha is equal to 0. Means at alpha is equal to 0 also, due to the camber effect, there will be a coefficient of moment due to aerodynamic center. So when given plus alpha, so dCm by d alpha is less than 0 or negative, there will be a positive lift. So there will be a CL naught and so CMAC. So due to this camber, this CMAC will be present in the cambered airfoil, but in the symmetrical airfoil, there will not be any moment in this case. Now, the Cm at alpha is equal to 0. So this Cm is equal to CMACW plus X bar CG minus XACW into CL naught. Here the CMAC is negative. So if it is since XAC is behind the CG, XAC is behind the CG, so XCG minus AC will be negative. So this value, because this CG is, AC is behind the CG. Okay, so this, since XAC, this is the AC and here is the CG. So this AC is behind the CG. So XCG, this is the XCG and this is the XAC. So XCG minus XAC will be negative. So in second term, XCG minus XCG CL0 will be negative and CM naught will be also negative. So slope will be negative and the intercept will be also negative. So this you can see at 0, but here it is a negative. So here CM naught is also negative. So in this we are meeting that CM naught is equal to negative and CM alpha is also negative. So but this is not meeting our stability criteria. So how to tackle such type of situation? CM due to horizontal tail. So we need to balance this aircraft. We need a tail. So how this horizontal tail will affect the CM of the aircraft? Let us see for the effect of horizontal tail. Taking tail is in symmetrical airfoil aft tail. CM is equal to CM naught plus CM alpha into alpha. To have statically stable, CM alpha dot alpha should be negative. Then what should be the CM naught at alpha is equal to 0? For symmetrical airfoil, tail, no lift and no CM naught or CM naught will be 0. So for the symmetrical, as it is shown in this diagram, the CM naught will be 0 for the symmetrical airfoil. But the CM naught should be positive for stability and large value needed. So how we will get? So in this case, your CM naught is also negative. It is like this. Here it is going like this. So how we will get? But the CM naught should be positive for stability and large value needed. How do I do that? That I need to give some setting angle of the tail called IT, or sometimes in some books it is IH. So this diagram you can see here. In this first diagram, number 1, it is at 0 angle of attack. But here we have made a minus IT, means nose is below the horizontal line. So this makes the CL downwards and this gives the CM in this direction. So you can see here in this plot, previously it was this one, but this is the second case. So this is the case 1. So you will get here CM naught is equal to greater than 0. So this tail is making the aircraft CM naught greater than 0. That is the purpose of the this horizontal tail, and it is very useful. At angle of attack alpha is equal to 0, CM naught should be greater than the 0 or it should be positive. So that is the effect of this horizontal tail. Now we have to discuss about what is the mean camber. It is always represented as a C bar here. So mean aerodynamic chord or the rectangular wing is same. So C is equal to C bar. For this black color, it is a rectangular wing in this diagram. So if the wing is given as a rectangular, so you have to take C, and this C is equal to C bar. For trapezoidal shape of the wing, C is equal to average of the chord as shown in the red color. So this red color, it is shown, this is the wing, and we have to take the average of this wing so that we can find out the C bar for aircraft. Pitching moment about y-axis. So if nose going up, it is a positive, and nose going down, it is a negative. Coefficient of pitching moment Cm is equal to pitching moment divided by half rho v square infinity and C bar plus alpha disturbance should generate pitching moment, that is nose down, negative, or dCm by d alpha should be less than 0. So to have the longitudinal static stability, the ratio of dCm by d alpha should be less than 0. In this way, it should work. Now, it is very important here to understand this wing contribution of aircraft and how mathematically we have to discuss. Just see here, in this case only we are discussing about the wing, and here in this diagram we have shown that how these wings are fixed to the fuselage. We are not discussing about the fuselage or tail or anything. We are only concerned with this line. We can make as a free body diagram in this way, and we have put this thing in two-dimensional. This red color, you can see that this is the aircraft wing. Let us find out the wing contribution for the longitudinal stability of the aircraft. And here you can see that the red color is shown as the wing, and here we have the leading edge and this is the trailing edge. This line, which is horizontal line, this horizontal line is called FRL, that is fuselage reference line. The center of gravity is CG is ZCG above from the horizontal, and from this leading edge, this is the location of XCG. XCG location horizontal is this and vertical is ZCG. This is the wing, red color. The flow is coming from this, and the angle of attack is defined as the chord line to the relative wind direction. So this is called wing angle of attack, and it is represented as a alpha W. The wing setting angle IT is called the wing setting angle, or IW here, IW. This is the IW here. So this IW means some angle which is above, it is positive, and if it is below, it is the negative. And this is the from relative wind to the horizontal, the angle between these two is called the alpha FRL. This velocity is touching this wing at aerodynamic center. At aerodynamic center, the lift LW is produced, and in the same direction, DW drag is produced. But these two things we can make in vertical and horizontal direction. So this vertical direction, this LW will be LW cos alpha W minus IW. This angle, alpha W minus IW, means alpha FRL. Same way here, for the drag also, drag will be for horizontal and for the vertical, and here also you will have one vertical and one horizontal. Okay, so I think and here one MAC, moment due to aerodynamic center. If it is cambered, it will some values will be there, and it is represented at the aerodynamic center. So I think this is the wing angle of attack, this is the wing setting IT, V is the relative wind, and this is the FRL direction. This is the aerodynamic center. From the leading edge to the aerodynamic center is XACW, where W subscript indicate as a wing. Okay, so I think all parameters I have covered. Now we will derive the equation for the coefficient of moment for this wing configuration, and we will see that how this wing is behaving as per the requirement. In free air, airplane will rotate with the center of gravity. We have aimed to find out dCm by d alpha. What will be the dCm by d alpha? That is our objective in magnitude and direction. Not only the magnitude, direction is also dCm by d alpha or Cm alpha we have to find out, and with the direction whether it is a positive or the negative. Let us write forces and moments L and D and M, taking moment with respect to center of gravity. So now pitching moment mcgw is equal to, very good, just you see, first we will see the horizontal and then we will see the vertical moments. So here LW, so this will be LW cos alpha W minus IW, and into this distance from here to here, because we are taking with respect to center of gravity. So how much is from here to here? This distance we have to see, and this distance is x cg minus x acw. This distance from here to here, this is, so from this force into this distance. Okay, so LW cos alpha W minus IW into xcg minus xacw plus. Now the vertical component of dW, this will be dW sine alpha W minus IW into xcg, same distance, xcg minus xacw plus here LW sine alpha W minus IW, another component, and this will be related to this in this direction, vertical direction, because it is in this direction. So this LW sine alpha W minus IW into ZCG minus DW cos alpha W minus IW into ZCG plus this moment MACW. Okay, so I think it is very much clear that all the forces into distance we have multiplied and we have got here this equation. Now we need to find the dCm by d alpha. So here we got m. So this m we have to find out the Cm. This Cm is equal to m by half rho v square s c bar. So now I am taking this first term LW cos alpha W minus IW xcg minus xac here, and I am dividing by half rho v square s c bar. So half rho v square s and c bar. So this LW by half rho v square is equal to CLW. So CLW cos alpha W minus IW, okay, into xcg minus xac by c bar, and so this will, we have got that CLW is equal to CLW cos alpha W minus IW xcg minus c bar minus xac by c bar. So this is one term, and same way we have to do divide half rho v square sc all the terms here, and then we will get here that we get the total coefficient of moment as given. CmCg is equal to CLW cos alpha W minus IW xcg minus xcg by c bar minus xec by c bar plus CDW sine alpha W minus IW xcg by c bar minus xac by W by c bar plus CLW sine alpha W minus IW ZCG by c minus CDW cos alpha W minus IW ZCG by c plus CMACW. So here we have to take some approximation. This alpha W minus IW is very small, so cos alpha W minus IW will be 1 and the sign will be 0. So wherever this sign is there, here one sign is here, one sign is here, all will go. ZCG is 0 because it is on the FRL. So this ZCG and this ZCG will go. So only we have left with two terms, this one and this one. So CmCg is equal to CLW cos CLW xCg minus c bar minus xac, because this has become 1. So xac by W by c bar CmACW. This is equal to 1. So here, but this CLW is equal to sum of the CL naught at 0 degree plus CL alpha into alpha. So here we will put CL naught plus CL alpha into alpha, XCG by C bar minus XACW by C bar plus CMACW. Here CL naught is equal to constant and CL alpha is changing with the alpha. So here we got that CMCG is equal to CM naught plus CM alpha into alpha, where CM naught is equal to CL naught XCG by C bar minus XAC by C bar plus CMAC, and CM alpha is equal to CL alpha W XCG by C bar minus XAC by C bar. So we got this two equation. One is for the CM naught and another is for CM alpha. So in this we can see that the distance between the center of gravity and the aerodynamic center is very important to find out these two parameters, that is equation A, that is the CM naught, and the equation B, CM alpha. Now we are going to discuss about the interpretation of this result. The designer to interpret these equations, what the message these equations give to get that CM naught is greater than 0, which component contribute. So CM naught, how we can get this CM naught greater than 0? If aerodynamic center of the wing is behind the CG, then CM alpha is less than 0. Okay, just you see, we have already discussed this thing. So if the aerodynamic center is here, AC, and here is CG. So if aerodynamic center is behind the AC, it will be going like this. So here CM alpha is less than 0, but this will give CM naught also less than 0. Okay? But what about CM naught? So if XAC is behind CG, so XAC minus XCG. So XAC minus XCG, if it is less than 0, that is perhaps is cambered airfoil wing. AC is located little ahead of the CG. So if it is the cambered airfoil and this is the CG and this is the AC, if like this, then it will be like this, and here CM naught will be greater than 0, and here it will do like this, CM naught greater than 0 for cambered airfoil. That is why we put the cambered airfoil for the wing, because our intention is to get this CM naught greater than 0. You won't see any main wing of the aircraft is symmetric, but you will get the horizontal tail or the vertical tail, you will get most of the time symmetric, but the main wing of the aircraft will always be cambered in such a way that aerodynamic center is little ahead to the center of gravity, so that a nose up tendency is maintained and a CM naught is positive. The effect of the CM naught positive is that it can give a trim angle here. This is the trim angle. This point, a positive trim angle is required. Positive trim angle is required for proper control of aircraft. So this is the interpretation, and as the engineer or designer of the aircraft, we should ensure that the CM naught should be positive and the slope CM alpha should be negative, and this can be achieved only when we use the cambered aerofoil on the main wing in such a way that aerodynamic center fall ahead of the center of gravity of the aircraft. If these things are happening, we can say that aircraft is statically stable if Cm naught is greater than 0 and Cm alpha is less than 0, or the slope of the Cm versus dCm d alpha is negative. So these are the interpretation, and we can see here again, if any this doubt exists here, we can very well see that the xcg here, xcg minus xac, this parameter is very important, and we can see here that this distance, as much you have more this distance, that much the moment will be high. That is why we should not put very far away the center of gravity. We should not put far away. Okay. So here just I am going to elaborate that this is the wing here, and this is the aerodynamic center, and this is the center of gravity. The distance between these two is called xcg minus xac. This xcg minus xac should not be more. Should not be more. If it is more, a huge amount of nose up tendency will be there, and this Cm naught will be very high. Okay, so if the Cm naught is very much high, here it will go like this. Trim angle will be high. So we should try to make a sufficient, but not so much high that trimming is also maybe difficult. So this we have to take care that this should not happen, and we should try to make things as easier as possible. So for the conclusion for the today, following topics were discussed in today's class. Cm naught and the Cm alpha were discussed. Symmetrical and cambered airfoil and its effect on stability also discussed. Wing contribution and the physics behind this is elaborated, and we have seen that how the Cm naught and Cm alpha, this we need a positive and this we need the negative, and how these two things can be made so that the longitudinal static stability of the aircraft can be achieved. This is only possible whenever we are using the main wing as a cambered airfoil like this. This is the cambered airfoil. If like this, AC will be ahead and CG will be behind. If it is like this, this will give a dCm by d alpha as a positive, but this will also give Cm naught also is equal to positive. But this dCm by d alpha, because we will keep very near, CG and AC will be very near, this amount we can counter by the tail, horizontal tail. This horizontal tail will make sure that dCm by d alpha is less than 0. Okay, so that is the purpose of the horizontal tail. Horizontal tail is used to counter the moment of the main wing. Otherwise, if you make the aerodynamic center behind the center of gravity, then Cm alpha will be negative of the wing, but same time Cm naught also will be negative, and that is not at all required. You cannot control the aircraft if such situation arises. So as a designer, we should try to make sure that aircraft should not go beyond the required level. So this we have discussed. Another we have discussed about the symmetrical and the cambered airfoil and its effect on the stability. So I have shown you here that for the cambered it is here, and for if it is a symmetrical airfoil like this will be Cm naught will be 0. So if you make the plot, it will go from here. So you cannot trim in this. You cannot trim. You can't trim the aircraft. So elevator will not be able to make the aircraft trim if you are using symmetrical wing. Okay, so this is the reason and why we are not using the symmetrical wing in main wing of the aircraft. I have also discussed about the contribution of the wing and these wings, about the physics of this wing, and I have also elaborated these things in detail. In next topic, I will take the tail contribution for longitudinal static stability. Just now I have discussed why the tail is required. But in the next class, I am going to discuss the tail contribution, and in tail, what are the important parameters and how much distance, what are the area of the tail and their aspect ratio and their dynamic ratios, neta h, sh, s, and these all parameters we will be discussing in due course of after 1 or 2 lectures we will be able to complete this tail contribution of this lecture. I am referring this book, these 2 textbooks, first one and second one, Yachout, TR et al., Introduction to Aircraft Flight Mechanics, AIAA Education Series, 2003, ISBN number 1-56347-577-4. Number 2, Nelson RC, Flight Stability and Automatic Control, second edition, Tata McGraw-Hill's, 2007, ISBN 0.07.066110. Itkin B and Reed, LD, Dynamics of Flight, third edition, John Wiley, 1998. This I am working on this. Thank you very much for joining the class, and I am ending here. Hope this class you might have liked it, and hope you will learn the effect of wing on the aircraft static longitudinal stability and how this wing is producing the Cm alpha positive or Cm naught positive or the negative, and how we can counter these things, and the effect of the tail will be discussed in due course of time. Thank you very much for joining the class.
Like, share and subscribe. Hit the bell icon for more updates.